polynomials and constant. But first, I want to tell you about something else. Maybe you've ever heard of Kroll, right? Well, so let me just tell you what one of these is. Definition. If R a domain R I want to specify three properties. One, R localized P is a Noetherian valuation domain. Minimum non-zero. So in other words, what do I mean by a minimal non-zero prime? I mean a prime ideal that is not zero, but there's no prime ideal between that and zero. So it's as small as you can get and not being zero. Some of the homework we did earlier shows that these things exist. Two, R is equal to the intersection of R localized at P. So if you take the family of all minimal non-zero primes and you intersect them, or their localizations, you get R. Notice we already know that R is the intersection of R localized at the maximal ideals, right? But see, this is a pretty strong thing because R localized at M in a certain sense is much smaller than R localized at P because you might have turned a lot more stuff into units, right? And so this is and also this last one, 3, every non-zero X in R is contained in only finitely many minimal non-zero primes. So this is sometimes it's referred to as finite character, although generally that means something a little bit different. But what this means, here's another interpretation. If you have any non-zero X in R, if you look at these Noetherian valuation domains, any X is a unit in all of these except for finitely many, right? That's what happens because if X is not in one of these prime ideals, it becomes a unit here. Since X is contained in only many, X is a non-unit in only finitely many of these R localized P's. This is called a Kroll domain. Let me make a couple of remarks without proof. If R is a Kroll domain, then one, R is interval closed. In fact, it's completely interval closed. And this actually follows immediately from this, that it's interval closed, right? Because each R localized P is in the Noetherian valuation domain. So it's interval closed, so it's an intersection of interval closed domains. Here's a couple of other facts. Number one, or number two, if m r plus sign equal to 1, then R is Dedekind. Of course, the dimension of R is 0 is field. So Kroll domains one might think of is a generalization of Dedekind. And of course, any Dedekind domain is a Kroll domain. There are Kroll domains that Dedekind that are not Dedekind. Like any UFD is a Kroll domain. Here, the family of, if it's a UFD, the family of the minimal primes are just generated by prime elements. Right? You can actually check that pretty easily. If you have a UFD, then you can let the family of minimal non-zero primes be the prime elements, the ideals generated by the prime elements. And all of these follow pretty easily. Are localized at P, it's prime element. That has to be an Noetherian valuation domain because in fact, when you localize that principal prime, you have to get a local PID. The intersection of this is not difficult to show. And of course, this one's also true because any non-zero X and R factors into a finite product of prime elements, and those are exactly the finite and many prime ideals that minimal prime ideals contain. Or Rx and R power X Kroll. This means that, so if R is a Kroll domain, so is this polynomial and power series extension. This makes Kroll a little bit more versatile than something like Dedekind, right? Because neither one of these, the only way that Rx or R power X is Dedekind is if R is a field. Because Dedekind domains have to be one dimensional or less, and every time you add another power series variable or another polynomial variable, you increase the dimension. So eventually you leave the playground of being Dedekind. But Kroll domains, you're good to go. So on one sense, Kroll domains generalize Dedekind because any Dedekind is Kroll. They generalize UFD because any UFD is Kroll. But of course, UFDs can be actually infinite dimensional, non-Noetherian, all kinds of things with their Kroll domains. Speaking of Noetherian, this will be used for later. If R is Noetherian, then R is Kroll domain if and only if R is, I know the characterization, this is probably not easy to see. That's kind of groovy because if you have any Noetherian domain, if it's integrally closed, it's Kroll. And of course, Kroll is always integrally closed. So if you restrict yourself to the world of Noetherian domain, then Kroll is equivalent to, then being a Kroll domain is equivalent to being an integrally closed domain. I hope it's fun. Okay. Kroll domains, like Dedekind domains, have an analog of the class group. And it turns out that it's not invertible ideals, it's something a little bit more general. Let me give you this theorem that we're going to use. Theorem. 1976, 1980. Zach's had two papers on this for some reason. The better paper, if you want to delve into such things, is the 1980 paper. It's in the Israel Journal of Math, I believe. 76 paper is in the Bulletin, the AMS. In fact, the AMS actually published good stuff in the Bulletin. Zach's wrote a paper. I think the title may have been half. These, by the way, these are the first sort of major references to the Carlos paper, which was written in 1969. Right. Well, one of the theorems Zach proves in this paper is the following. Let's suppose that R is a Kroll domain. Following conditions are below. Number one, Rx is an HFD. Number two, this is the generalization of the class group in the Kroll domain case, which I'm not going to talk about. This is exactly equal class group that you're used to if it's a one-dimensional Kroll domain, if it's dedicated, but it's slightly different in the higher dimension case. The proof of this theorem works exactly the way that the Carlitz theorem did. Now, one thing that may catch your mind is what went wrong for Carlitz, or what could go wrong with Carlitz proof. Carlitz proved HFD if and only if class number less than or 2 and rings of algebraic integers. Carlitz could have done it more generally. He did rings of algebraic integers because he needed two things. He needed a prime ideal in every class, and he needed the order of the class group to be finite. In fact, he didn't even really need that. He needed just a Schwarzian class group. But you know, rings of algebraic integers, they're important, they're sexy. So he said, oh, just look, this works in the ring of algebraic integers case. If you look back at Carlitz proof, it depended very heavily on, I would say, okay, look at this ideal class. I can pull a prime out of it, right? In general, in a Dedekind domain, or generally, I guess in a Kroll domain, you can't do this. You might have bad distribution. For example, you might have a class group Z6, right? And the only ideal class that contains prime ideals is the generated class. So the one bar class contains that, nothing else, right? This is a possibility, right? But here's a bit of magic that I wish we did have more time to talk about. But the prime ideals can be distributed in a Dedekind domain or a Kroll domain, sort of at random, right? With very little restriction. However, when you pass from R to its polynomial ring, it's sort of like they pick up the cards and distribute it again. Once you go, even if you have a random distribution here in this Kroll domain, when you pass to this Kroll domain, you get a prime ideal in every class. They're redistributed across the board. This allows that technique of Carlitz's theorem. So that's what Zach was doing back then. He said, hey, you know, this proved that Carlitz had, it works really good. What is really needed is a prime ideal in every class, and maybe torsion. And so here's what he came up with. It may not work for R, but it'll work for Rx because the primes are redistributed in a good enough way where there's a prime in every class, and I can mimic. That's essentially the step forward there. We're going to use this in a moment. I'm not even going to prove it, but I'm going to use it as a tool, which is also another thing. So let's talk about polynomials. So here's a question. You know the answer for it. Spoil this for me, but if R is an HFD, is Rx an HFD. Let me point out that this is true. HFD is replaced by UFD, FFD, BFD, ACC. It's a curiosity that it's not necessarily true if you replace it with atomic, which is again kind of too weird color TV, but it is what it is. But you would think that HFD being near the top of the food chain, right? I mean, it's a pretty strong coffee would maybe have this. So let me look at it. These actually, we threw number theory at this, and this is a UFD as a matter of fact. And in fact, some of you may have seen this in a number theory course before, where you show that the norm is actually the Euclidean norm. So no, it's Euclidean, right? And this is an HFD. And we actually showed this. Remember, if you remember correctly, really what it hinged on is it turned out that in this ring, everything that's irreducible is irreducible up here. And once you got that, you've got it in the death grip. Because take two irreducible factorizations of the same element, alpha 1 to alpha n is beta 1 to beta m. If you look at them up here, the alphas and the betas are still irreducible, making them prime, right? And so it's a prime factorization, so n and m are the same, so you've got HFD down here. Now, let me give you a frustrating example. And here's some notation back for you. If you look, notice that, of course, both of these things are an R, right? Oops. Okay, so let's multiply this out, shall we? Okay, so probably the middle ones, it looks like it's going to be 4x, right? And the final term is going to be 1 plus 3 is 4. Okay. And this is 2 times 2 times x squared plus x plus 1. Now, n elements to these variables. Let me see if I can talk you through that. 2 is irreducible in z square root of -3. In fact, the 2 is irreducible up here. It's a prime element up here. Since it's prime up here, there's no way it reduces down here. So 2 is an irreducible element of coefficient ring, so it has to be irreducible in polynomial. But it's this is irreducible because if you could factor it, the only units in z square root of -3 are plus and minus 1. So you would have to factor this into two monic polynomials, right? This would have to be x minus a, x minus b, right? But of course, this factors uniquely over q, right? In fact, I can tell you what the factors are. It's x minus omega bar, right? That's what this factorization has to be, is to reduce. But neither omega nor omega bar is in the coefficient ring, right? Because there's that pesky 2 in the denominator, which isn't here. So this one is irreducible because the only way it can factor is into two monic polynomials. So it has to have two roots, and the only roots to this thing are not in the ring. The last one to check is this. This is a degree 1 polynomial, right? So the only way you can factor that is into a degree 1 times a degree 0, right? So you'd have to pull a degree 0 out of this. But any factor that you can pull a degree 0 out of here has to divide 2. And the only thing that divides 2 are units and 2 itself, because it's irreducible. Okay, so if you try to jerk pull a unit out, that helps really. So if you try to pull the 2 out, you get these elements here, which are not in here. So is everybody convinced these three are irreducible elements? And look what we got here. 2 factors. So this is a dramatic example to show that even though the coefficient ring can have a half factorial property, it might fail for the polynomial ring. Can anybody identify what does it look like makes this fail? I could have reconciled some of the stuff if omega had been in the coefficient ring, right? And look at this polynomial in particular right here. Why is this irreducible? It's irreducible because it has roots up here that are not down there. That's really kind of the death sentence to this. It looks to me like what's killing this thing, what the machine that makes this example go, is the fact that this is an HFD that is not interval closed. So let me give you a little lemma as we kind of piece this together. And this is a simple lemma. Actually, I want to keep this factorization right here. Box here. Box.
Well, here you have 2x plus negative 1 minus which one's better?
What did I do?
Oh.
Oh, yeah. Absolutely. In the original, thank you. That's a. The right error. It should be that right there. But okay, so let me give you the following really cool lemma, which you might wonder what it's all about for a moment, but this basically tells you how things can sort of factor. So here, R is a domain, in some cases an HFD, but I'll let you know with quotient to OK. Lemma. I'm going to kind of justify this a little bit. Let P of X be irreducible in Rx. And R a non-zero element. If RPX is equal to R1, R2, up to, let's say, T F1, F2, up to Fk, with the RIs, yeah, actually, I didn't even really write it out like that. With RI, R, Fi in Rx, and the no Fi is monic. Seems to be, I mean, this seems to be, without the context here, I think this just seems to be me making up stuff to prove, right? I mean, who cares if any of this is mine, right? Well, let me tell you what the idea behind this is. Suppose I walk up to you on the street, give you some polynomial here, and it's irreducible, right? What this lemma is exploring is how this can break down. What if I can hit this polynomial with a constant and make it break, right? And in fact, we've seen this example right here. Here's a polynomial, right, over z radical 3 of x. You hit it with 4, and it's 2x minus 2 omega. That's 2x minus 2 omega bar. So see what I did? I hit this thing with a brick and it broke. Notice that none of these pieces are monic, right? And that's what this is for. So if you hit this with an appropriate constant that makes it split, right? Of course, if this were already irreducible over the quotient field, it wouldn't break down at all. But if you can hit this with a constant, make it break down into genuinely lower degrees, none of these people here can be monic, right? This, and basically writing down a bunch of equations here. So let's suppose that R P of X is R times Q. So this is, let me write this down this way. This is Rn xn 0. Let's suppose it's got a monic factor, xm, Sn minus 1, n minus 1, S1x plus S0. And so I guess if I put this together, it's 3n plus n. Okay, suppose that I can hit R times P, P of X with some constant, and it splits down into two factors, and one of them's mine, right? I want to get some kind of contradiction from this. And I'm going to call this last one, by the way, G1X, G of X, I guess. So this is an easy one to prove. It's kind of laughable in a way, but all it is just comparing coefficients. And I think we want to start with a constant term. No, I'll start with the leading term. So if I look at the leading term, I get Rn. So the leading term on this side is Rn, right? Leading term on the other side is Rqn plus m. Okay, let's do the degree n minus 1 term. Over here, I get Rn Sn minus 1 plus this should be n plus n minus 1, and so it should be Rn minus 1 Sm is equal to Rqn plus n minus 1. And I keep going until finally, so I don't get everything wrong, R0 plus R1 Sn minus 1 plus Rm S0 is equal to R. Now, what's the significance of this? Well, it's kind of a little stair-stepping thing, right? Because notice this line means that R divides Rn. And because R divides, so it's back to cascade. R divides Rn. Well, so R divides Rn, so it divides this term as well. Yeah, that's right. That's is 1. That would be an important thing. Right. Never showing up here. Right. So Sm, yeah, Sn is 1. So now R divides Rn, so it divides Rn plus 1. Minus 1. And you just keep cascading down, right? Now it divides n minus Rn minus 2. And finally, in this last one, R divides Rn, right, so R is divided all the way down, and so R0, right, there we go. So you cascade that sucker all the way down, and in particular, of course, R divides this. R divides every coefficient of g of x. So g1 of x, we'll just call g of x, because R divides every coefficient of this. So what we have, let's look back at this. We have R e of x is g1x, g2x, which is R G of X, 2 of X. Puts us the domain, we cancel R's on both sides. P of X is G of X, 2 of X, and this is a contradiction. Because P of X was the same thing. You're losing. So, so the moral of the story is, if you hit a polynomial with a constant and you make it break down into smaller degree factors, none of those smaller degree factors can be mined. This small observation is going to help us. So let me give you a if so that theorem explains why that example was z adjoint square root of -3, why its polynomial ring didn't work, because the coefficient ring is not integrally closed. Right? This is actually kind of exciting, because what it means is it's now easy to construct. It's easy to construct HFDs with polynomial rings or not. So, for example, these kinds of constructions are often not integrally closed. That right, but they're always HFDs, field plus bigger field, TFT. This is an HFD. In this case, it's not integrally closed. So it'll have the HFD property, but polynomial will not, right, by this theorem. So let's see why that's true. And by the way, this is the gateway, because this classifies all Noetherian polynomial HFDs, as a matter of fact. You'll see that in a moment. So let's assume close. Show X not HFD. So this is going to be the strategy. I'm going to assume that R is not integrally closed, and use that to show that polynomial ring is not an HFD. I'm also going to assume you can assume that R is an HFD, because otherwise you're just wasting your time. Because if it's not an HFD, then this polynomial ring has no chance, right? Because if you've got mismatched factorizations on your coefficients, that will again persist in the polynomial extension. So A is the quotient field of R. There exists omega in K minus R, such that omega is integral. So for example, in the example that we looked at, omega is an element of the quotient field of z adjoint square root of 3, and its integrality polynomial is x squared plus x plus 1, which actually showed up in our example. So we're going to try to key on that here. So let's suppose that omega is a root of monic irreducible polynomial that looks like this. Yeah. The let's call this P of X. The minimal monic polynomial. In Rx such that E omega. So it's got some monic polynomial first. I'm also going to write omega over S. Such that R and S have no non-unit factor in common. And this can certainly be done as R as an HFD. And here's the way you could do it, by the way, just to be curious, because among all the ways that you could write omega as R over S, and there might be many of them, pick the one with the smallest number of factors of R in the numerator, right? So, right, I mean, we all know fractions can be written zillions and zillions of ways, right? Among all the ways you can write omega, write it with R having the minimum number of irreducible factors top, right? None of these factors can cancel a factor downstairs in S. Why? Well, if there's a factor of the numerator and the denominator that cancel, then cancel them. And wouldn't you now have a shorter factorization of numerator representing the same element, right? So, you can certainly do this. Now, let me point out, this is kind of an interesting piece of it. Look at Sn, and I do mean that S, P of X. This is equal to, and I want us to justify this. How do I know this? Well, I know that P of X is X minus omega times some F of X. Everybody agree with that? Where F of X is actually in, may not be in Rx, it's in the quotient field, right? So Sn P of X, take one of your S's and put it here. And then take the other n minus one And notice that the n minus one factor, whatever this is, when I pull this x minus omega out, the biggest, because the degree of this is n, the biggest number of factors of s in the bottom that you can have here is n minus one. So this sort of renormalizes it. Everybody okay with that? Questions on that? So, and instead of calling this Sn f of x, where f of x may not be an Rx, I just call this q of x in Rx. Everybody cool with that? Now, I'm gonna start to count. So, let me make a couple of observations here about this factorization. Number of factors on left-hand side from at least one point of view is one for the p of x because it's irreducible, right? And then let me write this as n m plus one, where m is number of factors in S. Right? So just take the number of factors that you have in S, multiply that by n, so you get m, n, and then one for p of x, right? So from one point of view, I can factor it into this many irreducibles. When I say the number of factors, it's not clear that's well defined, but hopefully everybody knows what I'm talking about in the sense that there is an irreducible factorization that is of length nm plus one, right? M factors here to the n power, so there's nm of those plus one. Everybody okay? Number two, small observation. S x minus r is irreducible. And this is fairly simple. It's degree one. This is similar argument we did before. It's degree one. So the only way you can do anything is pull out degree zero. But here, R and S have no factor in common other than the unit, and so you can't do it. So that's irreducible. So let's try to count the factors in QX. Try to count that mess. The leading coefficient is leading coefficient is SN minus one, right? Because of course, P of X is monic, so its leading term is SCN, leading term of this is S, the leading term of this has to be SCN minus one. So let's assume that Q of X is equal to where each of the FIs is an irreducible. And Ri irreducible in R. And again, let me say this degree of Fi is bigger than zero. So I don't want there to be any ambiguity here. I mean, really polynomials that are linear or higher here. Because if they're not, I would put them over in the clump of R's. So here's the key step. Notice the lemma. Remember, this is a piece of the factorization of multiplying an irreducible by, none of these are monic. So we get the following equation. S, the leading coefficient of polynomial Q of X would be the product of the leading coefficients here. And of course, the degree zeros, they're their own leading coefficients. So this is L1, L2, LK times R1, R2, R2, where Li is leading coefficient of Fi and not the unit. So what does this give us? Notice that P plus T is less than or equal to M times N minus 1. What's N times N minus 1? It's the number of irreducible factors here, right? And remember, this factorization is going on down in R, and we know that R is an HFD. So this is a well-defined thing now. This has exactly N times N minus 1 irreducible factors, right? The difference here is nobody said any of, well, the RIs are irreducible, but the leading coefficients, maybe they are, maybe they're not, right? Nobody said the leading. So that means that the number of factors over here, you could have several irreducibles clumped together. So what's over here is less than or equal to what's on the other side, right? You hear that? So from this point of view, number of factors of S in EX could be, well, what should it be? It should be 1 for the SX minus R. And then it should be the number of irreducible factors of Q of X, which is K plus T. Yes, there we go. The number of irreducible factors of S and PX is this, right? Because 1, and then we've got to count the factors of Q of X, which is K plus T. Now that is oops, that's less than or equal to this, which is less than or equal to M n plus 1. R of X to be an HFD this has to be one big fat string of equalities. Right, so you gotta have all, so in particular, what you need for this to be an equality, this is one plus mn minus m equals 0. Right, that's the only way that I can do it, but m is number of irreducible factors in S. Therefore, S is a unit in R. So omega is R over S is in R, and there's your contradiction. So there you go. For you to have a polynomial HFD, a polynomial of the HFD form is absolutely necessary that it be an HFD that is in fact integrally closed. So let me give you a corollary. And this basically tells, and I'll tell you what's open about this today. This basically tells you what you need to know, corollary. Let's suppose that R is an Noetherian ring, following equivalent. Number one, R is a Kroll domain. We have CLR less than or equal to. RX is an HFD. R X1, X2, X. So this gives basically the entire classification of if you have a Noetherian ring, polynomial rings in HFD, it's Kroll domain, class number less than or equal to, period. So the equivalence of these is the important one. Suppose RX is an HFD. As then R is integrally closed. By what we just showed, right? I mean, that's what we went to all the trouble showing. So R is Noetherian and integrally closed. So R is a Kroll domain. By Zach's, R is a Kroll domain. So we've shown this Kroll domain. Zach's showed that this Kroll domain class number less than, because you know that RX is an HFD. And the other direction, two implies one, I guess. One implies two is Zach's. So Zach showed that if you have any Kroll domain class number less than or equal to 2, there's a polynomial reason HFD. So we bootstrap that in both directions, but this gives classification. And once you have this, then you're good to go from here on. Because another fact that I didn't tell you is that if you have R is a crawl and class groups, both R and RX are isomorphic. So once you have this, then you can just go by induction, because now if RX is an HFD, then RX is a crawl domain, it's still got class member less center to add another variable. Okay. Any questions on that? Okay, so let's prove the same thing for power series. Only there's gonna be a problem. I see problems sprinkled around here. Right, I mean, just look at this. Don't really expect there to be a leading term, do I? Right? That might be problematic. But, I mean, at least we've still got our counterexample, right? And, you know, if you have a ring, an integral domain, and it loses the half factorial property in polynomial extension, you surely got to use it in the power, lose its power to extension, doesn't it? See, not. Because you have this. Big counterexample here. 2x minus 1 like 3. 2x minus 1 plus like 3 is over x squared. That is minus 1. Oh, I sure did. Yeah, wrong in a different place. So certainly this room's got to fail to be the power series has to fail basically, because any polynomial is a power series, right? So I should be able to bootstrap this example. But I see there's trouble. I can't bootstrap this example. Why not? What's wrong with it? That is correct. This nice little friendly irreducible polynomial is now a unit in power series. So basically that disappears because it's a unit. I've got 1, 2 factors over here, 1, 2 here. Well, worry not. Maybe we can, this may be an extremely bad choice, but it's not. And this is even weirder than color TV. This one is an HFD. And I think that's really weird because you pass from coefficient ring to polynomial ring and you lose it. And then you complete your broken thing and it repairs it, which is very strange. This is actually, I'm sorry Grant's not here because actually, here's the theorem. That is due a good deal to your colleague, soon to be doctor, depending on the job market, moles. Yeah, R is a quadratic. If R is an order inside a quadratic ring of integers. And actually, more than what I'm going to say is true. Yeah. Or power X. It's an order inside a quadratic group of integers. That is an HFD. And although we proved earlier in this class that there was only one of them in the imaginary quadratic, they exist in abundance. They exist in abundance, and in fact, first I should say this, I have my hands on a paper written by somebody that does kind of this analytic kind of number theory. It's recently been shown that in fact, there are infinitely many real quadratic fields that contain infinitely many HFDs inside of them, using some really nice number theoretic arguments. Then R power X is an HFD. It turns out it's fairly easy to prove that the integral closure R bar power X is an HFD. And inside it, if you have inside it the quadratic ring of integers, an HFD order inside there, then it's power sheet ring. Even though if R is strictly contained inside of R bar, that'll never work for polynomials, because if R is strictly contained inside of R bar, then it cannot be infinitely closed. Okay, the proof of this is, I actually first proved this for the special case Z of joint square root -3, and it's in an expository paper that I wrote, and the proof is kind of complicated. Grant was able to really kind of smooth things out quite a bit, I think, and get a lot more stuff, so that's good. All right, any questions on that? Any questions? Well, thank you for being a very fun class. I've enjoyed it, and I'm done torturing you.